Welcome back. 20 more questions for you today, themed around AI search result limits, inference table logging, and MLflow evaluation. 10 seconds per question on the timer. Pause when you need to. Let's see how the patterns land this round. Let us keep moving. Question 1. One detail changes the answer. A generative AI engineer at Pembry Systems configured an inference table on a production model serving endpoint to capture all requests and responses for compliance auditing. A data engineer later modified the inference table schema to add 2 columns required by a downstream analytics pipeline. The compliance team subsequently discovered a logging gap covering the 3 weeks since the schema was changed. What caused this gap? Select 1. Review the answer choices on screen. The correct answer is option B. Schema change severs the internal write path for good. Databricks inference tables stop logging, or become corrupted, whenever the table schema is changed after the serving endpoint is configured, when the table is renamed, or when the table is deleted. The logging pipeline depends on a fixed schema precisely matching the columns Databricks writes, Databricks_request_i.d, client_request_i.d, date, timestamp_ms, status_code, sampling_fraction, execution_time_ms, request, response, and request_metadata. Altering that schema breaks the internal write path and logging stops indefinitely. The correct approach is to leave the inference table schema untouched and apply downstream transformations or column additions in a separate ETL process. There is no automatic suspension period or write buffer rebuild behavior triggered by schema changes. The 10 MB payload limit causes individual oversized payloads to be dropped, not all subsequent logging to cease. Inference tables do not implement a rolling retention window or automatically purge data following schema modifications. Let's slow down here. This one is a quiet gotcha that trips up a lot of engineers. Imagine your compliance team is relying on an inference table to log every AI request. It's been running fine for months. Then a data engineer adds 2 new columns to help a downstream pipeline. Sounds harmless, right? Here's the trap. Databricks owns the table's schema. It writes to exactly 10 fixed columns, things like request ID, timestamp, and response payload. The moment you add a column, the write pipeline sees a mismatch. The endpoint marks logging as failed. Logging stops silently. No alert fires. No error email. That's how you lose 3 weeks of compliance data without noticing. The fix? Leave the inference table untouched. Add custom columns in a separate ETL step downstream. Time for another one. Question 2. Watch the exact wording. A generative AI engineer is building a re-ranking pipeline for a legal research assistant using Databricks AI Search. Each query must retrieve up to 150 candidate documents that score on both keyword presence and semantic similarity before being passed to a cross-encoder re-ranker. The engineer wants a single retrieval call without custom external components. Which statement correctly describes the search approach and its documented constraints? Select 1. Review the answer choices on screen. The correct answer is option A. Only hybrid combines keyword and semantic in one call. Hybrid search is the correct choice because it natively combines BM25 keyword matching with semantic similarity scoring in a single retrieval call, directly matching the requirement for both keyword and semantic signals. Its documented hard cap of 200 results per query comfortably accommodates 150 candidates without pagination, custom result merging, or any external components. ANN queries via the Python SDK do not natively incorporate keyword scoring. Providing both keyword and semantic signals from ANN alone would require a separate BM25 layer with custom reciprocal rank fusion. Additionally, The 10,000 result figure represents the maximum records that can be assembled through paginated calls across multiple pages, not the result of a single non-paginated query. The performance guide explicitly recommends keeping num_results in the 10 to 100 range, noting that a 10 times increase in num_results can double query latency and reduce QPS capacity by 3 times. The 200 result cap applies specifically to hybrid search and full-text search, not to all ANN queries uniformly. The SQL vector_search function imposes a separate and lower cap of 100 results on that specific SQL interface, and this limit cannot be overridden. Claiming that either a shared 200 cap or a shared 100 cap governs both search modes conflates two distinct limits that apply to different interfaces and search types. Since hybrid search's 200 result cap is above the required 150 candidates, the engineer can satisfy the requirement with a single hybrid search call and no architectural changes. Time for another one. Question 3. The trap is partial correctness. A generative AI engineer at Oakhurst Analytics has enabled an inference table on a production conversational AI endpoint. They are building a monitoring dashboard that must display 3 pieces of information for each logged interaction: the exact time the request arrived at the endpoint, the HTTP response code the endpoint returned, and the total processing time in milliseconds from receipt to response. Which 3 inference table columns should the engineer query for this dashboard? Select 3. Review the answer choices on screen. The correct answers are option A, option B, and option C. Each dashboard metric maps to exactly one table column. Timestamp_ms records the Unix timestamp in milliseconds, at which the request arrived at the endpoint, directly satisfying the arrival time requirement. Status_code captures the HTTP response code returned for each interaction, which is the standard signal for whether the endpoint succeeded or encountered an error condition. Execution_time_ms records the total number of milliseconds the endpoint spent processing each request from receipt through response, satisfying the processing duration requirement. Sampling_fraction is a configuration parameter reflecting the proportion of requests being captured rather than a per-request measurement, so it contains no timing or status information useful for this dashboard. Client_request_i.d is an optional identifier supplied by the calling application to correlate requests with the client's own records. It conveys no timing or HTTP status information. Request_metadata contains additional context about the request origin but does not record arrival timestamps, HTTP response codes, or per-request processing durations. Ready. Question 4. Several choices sound plausible. A generative AI engineer at Prism Analytics is building a product recommendation assistant using feature serving. The feature spec must perform 2 distinct operations: retrieve pre-computed user affinity scores stored in a feature table and apply a real-time discount tier calculation, using a Unity catalog function that takes the user's membership duration as input. Which 2 feature spec components support these respective operations? Select 2. Review the answer choices on screen. The correct answers are option A and option C. Pre-stored versus on-demand. The component names say it. A feature spec is constructed from 2 complementary component types that cover the 2 fundamental modes of feature delivery. Feature lookup retrieves pre-materialized column values from a feature table at inference time using entity keys to fetch the correct row for each request. This handles the pre-computed user affinity scores that were calculated offline and stored. Feature function invokes a Unity catalog function at serving time to compute values on demand from request time inputs. This handles the discount tier calculation that depends on membership duration provided at inference time. Feature stream, feature join, and feature cache are not valid feature spec component types in the Databricks Feature Engineering SDK, and do not exist as configurable components of a feature spec. Ready. Question 5. Do not answer a different question. A generative AI engineer is implementing an LLM as judge evaluation pipeline in MLflow to score how relevant retrieved chunks are to user queries in a RAG system. They want to align their scoring rubric with MLflow's built-in judge behavior to ensure comparability across experiments. Which relevant scoring scale should they adopt? Select one. Review the answer choices on screen. The correct answer is option B. 0 anchors the scale. MLflow's built-in rubric starts there. MLflow's built-in LLM judges use a 4-point relevance scale where 0 indicates no relevance, 1 indicates partial relevance, 2 indicates relevance, and 3 indicates high relevance. Adopting this scale ensures that custom evaluation pipelines and MLflow's native judges produce scores on the same range, enabling direct comparison across experiments and calibration against MLflow's tracked Cohen's kappa and F1 scores relative to human judgment. A binary scale loses the granularity needed to distinguish marginally relevant from highly relevant chunks. The 3-point scale starting at 1 omits the 0 irrelevant state present in MLflow's built-in rubric. The 5-point scale introduces a step the built-in judges do not use, making cross-experiment score comparisons inconsistent. Let's slow down here. MLflow's relevant scale trips people up, and the exam knows it. Picture your RAG system returning 100 chunks for a tax law question. Some chunks mention the topic but don't answer it. Some are perfect. Binary scoring, yes or no, can't tell those apart. MLflow's built-in judge uses 4 levels, 0 through 3. 0 means completely off topic, 1 means related but not useful, 2 means it genuinely helps, 3 means it nails it. When you write a custom judge, use these exact 4 levels. Your scores go straight into MLflow's experiment tracker, no conversion needed. The trap: the 3-point scale skips 0, and the 5-point scale adds a level MLflow doesn't use. Match the built-in scale exactly, that's the point. Inference tables break permanently when their schema changes. Hybrid search is hard-capped at 200 results per query. MLflow's built-in relevance judges use a 0-anchored 4-point scale, not binary, not like it. Let us switch gears. Question 6. The obvious answer may be bait. A generative AI engineer at Meridian Research finishes training a language model and calls MLflow.register_model without specifying a registry URI. A colleague asks where the model will be registered and what governance capabilities that location provides. Which statement accurately describes the outcome when using MLflow 3 defaults? Select one. Review the answer choices on screen. The correct answer is option B. MLflow 3 silently changed where models land by default. In MLflow 3, the default registry URI is Databricks UC, which points to the Unity Catalog model registry. When MLflow.register_model is called without specifying a registry URI, the model is automatically registered in Unity Catalog. This provides the full Unity Catalog governance stack. Models are organized using the 3-level namespace structure of catalog, schema, and model name. Lineage tracking links the registered model to the training data, experiments, and runs that produced it, and fine-grained access controls allow permissions to be set at the catalog, schema, or individual model level. The Databricks Workspace Model Registry was the default in earlier MLflow versions, but is no longer the default in MLflow 3. The registration call does not fail for a missing URI because the default is applied automatically. DBFS is an artifact storage location for files such as checkpoints and binaries, not a model registry, and no administrator promotion step is part of the standard MLflow registration workflow. Let us switch gears. Question 7. follow the operational constraint. A generative AI engineer at Whitmore Analytics has tuned 2 prompt templates for a customer support application and wants to determine which produces better responses. Because both templates generate consistently high-quality outputs, per response scoring tends to cluster near the top of the scale, making the 2 templates appear indistinguishable. Which LLM as judge methodology should the engineer use to surface meaningful quality differences? Select one. Review the answer choices on screen. The correct answer is option C. Relative judgment surfaces gaps that point scoring masks. Pairwise comparison is purpose-built for directly contrasting 2 candidate outputs. By presenting the query and both responses to the judge simultaneously and asking it to select the better one, this methodology captures relative quality differences and produces judgments that align more closely with human preference than independent scoring does. Single output scoring evaluates each response in isolation, which introduces inter-run variance and score compression near the top of the scale. When 2 templates produce similarly strong responses, these aggregate scores often fail to discriminate between them reliably. Retrieval groundedness measures whether a response is supported by retrieved context and is a RAG faithfulness metric, not a mechanism for comparing prompt template quality. DCG-AD10 is a retrieval quality metric that measures ranking relevance of retrieved documents and is not applicable to evaluating the quality of generated text outputs. Let us switch gears. We're on question 8. A data engineering team plans to deprecate a feature table containing customer transaction aggregates. Before removing it, they need to identify every model currently consuming features from this table to assess downstream impact. Where should they look to find this information? Select one. Review the answer choices on screen. The correct answer is option D. Lineage lives in Unity Catalog, not MLflow or SQL history. Databricks Feature Engineering stores lineage metadata in Unity Catalog that links feature tables to the model versions trained using them. The lineage view surfaces which models consumed features from a given table, enabling teams to assess downstream impact before deprecating or modifying that table. The MLflow experiments UI tracks run parameters and metrics, but does not record feature table consumption as structured lineage. Runs may reference table names by convention, but there is no guaranteed programmatic linkage. Model serving endpoint logs capture inference time request payloads, not training time feature dependencies that were established when models were built. SQL query history records ad hoc analytical queries executed by users and does not track feature consumption in the context of model training workflows. Keep your focus here. Question 9. Choose for this case. Not every case. A generative AI engineer at Riverside Medical is building an evaluation framework for a clinical decision support RAG system. They need to measure 2 things: whether all relevant clinical guidelines are captured in retrieved results, and how well those results are ranked by clinical importance. Which 2 retrieval metrics should be included in the evaluation suite? Select 2. Review the answer choices on screen. The correct answers are option B and option C. Completeness and ranking order need 2 different metrics. Recall that K directly measures retrieval completeness. What fraction of all known relevant clinical guidelines appeared in the top K results? In a clinical decision support context, missing a relevant guideline has potential patient safety consequences, making completeness the primary concern. NDCG-AD10 measures ranking quality by assigning more credit to relevant documents that surface earlier in the result list, which helps ensure the most critical guidelines appear first for practitioners. Precision-AD10 measures what fraction of retrieved documents are relevant, but does not penalize for failing to retrieve relevant guidelines that were omitted, making it insufficient as the sole measure for a completeness-focused clinical application. Perplexity is a language model training time metric measuring token prediction uncertainty and plays no role in retrieval evaluation. Blur score evaluates text generation quality through n-gram overlap and does not evaluate retrieval behavior at all. Alright, question 10. Separate context from noise. A generative AI engineer is building an LLM-powered market summary assistant for a financial trading firm. The assistant must reference live asset prices at the moment each summary is generated, and those prices are updated multiple times per second by upstream pipelines on the platform. Which Databricks service should the engineer use to supply live asset prices to the assistant at inference time? Select one. Review the answer choices on screen. The correct answer is option A. Live prices at inference time. Only feature serving fits. Feature serving exposes pre-computed and continuously updated values through a low-latency, auto-scaling endpoint that an application can query at inference time to inject fresh data into an LLM prompt. For prices that update multiple times per second, feature serving is specifically designed to serve these real-time features. Foundation model APIs provide the language model for text generation but carry no live market data of their own. AutoML automates model training and selection, which is unrelated to serving real-time features at inference time. Databricks IQ is a platform assistant capability that helps engineers work within the Databricks environment and cannot serve live pricing data to production applications. MLflow 3 defaults to Unity Catalog, not the workspace registry. Pairwise comparison outperforms independent scoring when outputs cluster at the top. Feature serving is purpose-built to inject sub-second values at inference time. Alright, question 11. Do not answer a different question. A generative AI engineer at Trentum Finance is registering a fraud detection model to Unity Catalog. The workspace MLflow registry URI is configured as Databricks UC. The target catalog is prod_catalog, the schema is risk_models, and the model should be named fraud_classifier. What is the correct string to pass as the model name argument to MLflow.register_model? Select one. Review the answer choices on screen. The correct answer is option C. Dots only. Forward slashes and colons both fail here. Unity Catalog enforces a 3-level delimited namespace for every managed object, including registered models. The required format is catalog.schema.model_name, so prod_catalog.risk_models.fraud_classifier is the correct argument. Providing only the model name fraud_classifier without catalog and schema qualifiers either resolves to the legacy workspace level registry or fails outright when MLflow is configured with the Databricks UC registry URI, which is the default in MLflow 3. Forward slashes are path separators in file systems and object storage, but are not valid namespace separators in Unity Catalog syntax. Passing them causes the registration call to fail with a parse error. Colons are equally invalid as namespace delimiters for Unity Catalog objects and produce the same failure. Okay. Question 12. Compare what is asked to what is offered. A generative AI engineer at a datum is preparing a delta table to serve as the source for a new AI search index in a product catalog application. The source table uses a primary key column named _i.d to uniquely identify each product. When the engineer attempts to create the delta sync index, the operation fails with a validation error. What is the correct resolution? Select one. Review the answer choices on screen. The correct answer is option D. _i.d is reserved across every AI search index type. The column name _i.d is reserved in Databricks AI search and cannot be used as a field in any index type. Renaming the column to a non-reserved name in the source delta table before creating the index is the direct and only valid resolution. Switching to a direct access index does not help because the reservation applies to both index types, and direct access indexes must be created via REST API or SDK regardless of column names. Enabling change data feed is a prerequisite for delta sync indexes generally, but has no effect on column naming restrictions. Composite key configurations do not override the reserved status of the _i.d column name and will not allow index creation to proceed. This one looks like a setup problem. It's actually a naming collision. Let me show you why. Imagine you're setting up a searchable product catalog with 50,000 items. You point Databricks AI search at your delta table and hit a validation error immediately. The hidden trap is the column named _i.d. AI search reserves that name internally. It uses _i.d as its own system field. You can't escape by switching index types. Direct access indexes block the same name. Enabling change data feed? That's a real delta sync prerequisite, but it does nothing about column names. The question drops validation error as a clue. This is an engine-level hard stop. The only door out is renaming the column. That's the whole exam point here. Okay, question 13. The clue is not in the service name. A generative AI engineer at Trident AI has enabled an inference table on a high-traffic serving endpoint that processes approximately 500,000 requests per day. Storing every request is unnecessary, and the team wants to capture a statistically representative 20% sample of all incoming traffic for monitoring. How should the sampling parameter be configured? Select one. Review the answer choices on screen. The correct answer is option C. Fraction of 1, not a percentage integer, 0.2 not 20. The sampling underscore fraction parameter for Databricks inference tables accepts a value between 0 and 1, where 1 represents 100% capture of all requests. To capture exactly 20% of incoming traffic, the value must be set to 0.2. A value of 20 or 20.0 falls outside the valid 0 to 1 range and is not accepted. A value of 0.02 would capture only 2% of traffic, 1/10 of the desired rate, because the parameter uses a fractional decimal scale rather than a whole number percentage scale. The engineer must express the desired capture rate as a decimal fraction of 1 rather than as a percentage integer. Here we go. Question 14. Watch for the hidden requirement. A generative AI engineer at Helix Genomics has built an AI search standard endpoint containing 1.4 billion vector embeddings representing molecular sequence data. Query latency currently meets production requirements, but the daily indexing pipeline takes an unacceptably long time to synchronize new data. A colleague recommends migrating to a storage-optimized endpoint. The engineer wants to understand the performance trade-off before committing. Which statement accurately describes the expected difference? Select one. Review the answer choices on screen. The correct answer is option A. Faster indexing always costs extra query latency here. Storage-optimized endpoints are specifically designed for very large vector corpora exceeding what standard endpoints handle efficiently. They support more than 1 billion vectors and deliver 10 to 20 times faster indexing compared to standard endpoints, which directly addresses the slow daily synchronization pipeline. The known trade-off is an approximate 250 milliseconds increase in per-query latency. Since the engineer's current query latency already meets requirements, absorbing this modest increase may be acceptable for the significant indexing speed gain. Storage-optimized endpoints do not eliminate query latency. They exchange a small amount of additional query time for dramatically faster indexing throughput. The faster indexing is achieved through a different storage architecture, not by reducing embedding dimensions. The maximum number of indexes per endpoint remains 50 for both endpoint types, and is not part of the storage-optimized trade-off. Let's slow down on this one. The storage-optimized trade-off is exactly what the exam is testing. Imagine your daily indexing job takes 4 hours. That's the situation at Helix Genomics, 1.4 billion molecular vectors to resync every day. Standard endpoints get slow at that scale. Storage-optimized endpoints fix this. They support more than 1 billion vectors. They also index 10 to 20 times faster. That 4-hour job might shrink to under 30 minutes. The catch? Every query costs about 250 milliseconds extra. If your current query latency already meets production requirements, that's an easy trade. The exam trap is thinking you get all this speed for free. You don't. Faster indexing costs a little more on the query side. Next up, question 15. Picture the scenario first. A generative AI engineer at Clearfield Insurance is deploying an LLM assistant for claims adjusters. Regulatory requirements prohibit personally identifiable information such as email addresses, social security numbers, and phone numbers from appearing in requests sent to the model or in responses returned to adjusters. The team wants enforcement at the infrastructure layer without modifying any application code. Which AI gateway feature should they configure? Select one. Review the answer choices on screen. The correct answer is option B. Infrastructure layer PII enforcement is the gateway's job. AI gateways PII detection and redaction guardrails are designed precisely for this scenario. When enabled, the guardrail scans both incoming requests and outgoing responses for recognized PII patterns including email addresses, social security numbers, and phone numbers, then automatically replaces them with neutral placeholders before content is forwarded to the model or returned to the user. This enforcement happens at the gateway layer with no application code changes required. Rate limiting controls how many requests a user can send per unit of time. It does not inspect content for PII, and cannot prevent sensitive data from reaching the model. Traffic splitting is a routing mechanism for load distribution or A/B testing, and performs no content inspection or redaction. Safety filters address harmful content categories such as hate speech and violence, which serve a different compliance purpose and are unrelated to PII protection. Unity catalog model names are always delimited at 3 levels. _ID is reserved in every AI search index type. Storage-optimized endpoints trade roughly 250 milliseconds of query time for up to 20x faster indexing throughput. Next up, question 16. Look for the limiting phrase. A generative AI engineer at Contasso is logging a fine-tuned model's checkpoint files as artifacts in an MLflow experiment. The total size of one checkpoint file is approximately 7 gigabytes. When the engineer calls mlflow.log_artifact on the file, the operation fails. What is the most likely cause and the correct resolution? Select one. Review the answer choices on screen. The correct answer is option B. 5 gigabytes is the hard ceiling per artifact file. MLflow on Databricks enforces a 5 gigabytes limit per artifact file for upload and download operations. A 7 gigabytes checkpoint file exceeds this ceiling, which causes the log_artifact call to fail. The resolution is to either split the checkpoint into files each under 5 gigabytes, or configure the experiment to use a remote artifact store, such as Unity Catalog Volumes or Amazon S3, that handles large objects natively without the MLflow per file size constraint. MLflow experiments do not have a configurable storage quota, and deleting and recreating an experiment does not change any file size limits. MLflow fully supports logging binary artifacts including model weights, saved model directories, and other large files. Artifact logging is equally available in both development experiments and for production-registered models on the platform. Now, question 17. Eliminate before you select. A generative AI engineer at Foxwood Analytics is building a RAG application that must answer questions drawing on both company policy documents stored as PDFs and current product inventory data stored in a relational database. Which two retrieval mechanisms should they configure to handle both data sources appropriately? Select 2. Review the answer choices on screen. The correct answers are option A and option C. Match the retrieval tool to the data structure type. RAG applications must match the retrieval mechanism to the data structure. Unstructured documents such as PDFs are best served by chunking the content, embedding the chunks, and storing them in an AI search vector index. This enables semantic similarity retrieval that surfaces contextually relevant policy passages in response to natural language queries. Structured data in a relational database is best accessed through a SQL-based retrieval tool that queries the database directly at inference time, returning precise and current rows based on exact conditions such as inventory counts or SKU lookups, rather than semantic proximity. Exporting the inventory database to PDF format destroys the structured nature of the data, eliminates the ability to perform precise filtering or aggregation queries, and introduces data staleness. Feature serving is designed for pre-materialized real-time features, such as live metrics or model scores, not for full-text document retrieval or ad hoc SQL queries against operational inventory databases. A BM25-only keyword index cannot substitute for semantic vector search over unstructured PDF content, and cannot replace SQL for structured queries that require filtering, joins, or aggregations over inventory records. Now, question 18. Use elimination aggressively. A generative AI engineer at Cordova Financial is building a RAG application for investment analysts. The application must answer questions using both unstructured equity research reports stored as PDFs and structured revenue and earnings data stored in a relational database. The engineer needs to design the retrieval layer to handle both data types correctly. Which two approaches should they take? Select 2. Review the answer choices on screen. The correct answers are option A and option C. Embedding table rows into vectors destroys SQL precision. Unstructured documents such as PDF research reports are best handled through chunking, embedding, and semantic search in AI search, enabling retrieval of relevant passages based on query similarity. Structured data in relational databases is best queried using SQL at inference time, which preserves the precision, filtering, and aggregation capabilities that tabular data requires. Embedding structured database rows into a vector index loses the exact value semantics and join capabilities that SQL provides, degrading accuracy for numerical queries. Converting structured tables to plain text discards the relational structure and makes precise numerical retrieval unreliable. Storing everything in a volume with full text search removes both the semantic matching capability needed for PDFs and the relational querying capability required for earnings data. Let us keep moving. Question 19. Watch for must, most, least, or except. A generative AI engineer at Hartwell Commerce is building a product recommendation engine backed by Databricks AI Search. The team wants to implement both keyword and semantic search simultaneously to maximize result coverage for a downstream re-ranking model. The engineer notices that the ANN-only query returns significantly more candidate results than the hybrid search query, even with identical num_results settings. Which statement correctly explains this behavior? Select 1. Review the answer choices on screen. The correct answer is option D. Need more than 200 candidates? ANN only, not hybrid. Databricks AI Search enforces different per-query result caps depending on the query modality. ANN-only queries support up to 10,000 results per call, while hybrid search queries and full-text searches are capped at 200 results. Teams that need large candidate sets for downstream re-ranking must use ANN-only retrieval rather than hybrid search. There is no shared 200 result cap across all query types. The HNSW algorithm does operate on bounded graph neighborhoods, but the result cap distinction is an architectural limit on the query modality, not a direct consequence of the algorithm's graph traversal. Result limits are fixed per query type and are not configurable on a per-endpoint basis. Slow down here. ANN and hybrid search don't share the same result ceiling, and that's the whole question. Imagine you're building a product recommender for Hartwell Commerce. You want 500 candidate items for your re-ranker to score. You set num_results to 500, and your hybrid search query comes back with only 200. Here's why. Hybrid search and full-text search are hard capped at 200 results per query. That's a fixed architectural limit, not a tunable setting. But ANN queries, that's approximate nearest neighbor, pure vector search, support up to 10,000 results. So if your re-ranker needs a big candidate pool, hybrid search quietly shortchanges you at 200. The trap is assuming both query modes share the same ceiling. They don't, and that's exactly what this question tests. Let us keep moving. Here's question 20. A generative AI engineer at Briarwood Capital built a RAG application that answers questions about company financial disclosures. During a quality review, analysts report that some answers contain specific figures not present in the retrieved document excerpts supplied to the LLM. The team needs a built-in MLflow scorer that directly measures whether generated answers stay within the factual bounds of the retrieved source material. Which scorer should they use? Select one. Review the answer choices on screen. The correct answer is option D. Faithfulness scores the answer against retrieved context only. Faithfulness is specifically designed to measure how factually consistent a generated output is with the provided context. A high faithfulness score means the answer stays within information present in the retrieved document excerpts, while a low score signals the model is contradicting or ignoring the retrieved context and introducing content not grounded in the source, exactly the pattern where analysts observe figures absent from retrieved material. Answer_relevance evaluates whether the output is topically appropriate to the input question, but explicitly ignores the retrieved context, so it cannot detect when an answer introduces hallucinated information absent from the retrieval results. Answer_similarity compares the generated output against a labeled ground truth reference answer, which the team does not possess for every financial disclosure query. Answer_correctness also requires labeled ground truth answers to measure factual accuracy, and is therefore unsuitable when the only available reference material is the retrieved context itself. 3 takeaways from this session. First, inference table schema changes permanently break logging, apply transformations downstream, never alter the table itself. Second, hybrid search caps at 200 results per query, build large re-ranking candidate pools with ANN-only queries instead. Third, MLflow 3 defaults to Unity Catalog. Faithfulness needs only retrieved context, not labeled ground truth answers. This batch is built around precise constraints: a 200 result ceiling, a reserved column that breaks indexes, a schema touch that silently halts logging. Memorize the exact limits. The exam doesn't reward close enough.